Good morning, everyone. We'll go ahead and get started as it's top of the hour here. Thank you for joining us today. My name is Diane Lechner. I'm the Vice President of Sales here at Midland Scientific, and we're very excited to have Inorganic Ventures joining us for the webinar today on environmental analysis by ICP-MS. We have Brian Alexander that's joining us here. Dr. Brian Alexander, he's an earth scientist specializing in geochemistry. So his research is focused on radiogenic isotope and rare earth element studies of natural waters and chemical sediments, as well as trace metal analysis using ICP techniques. He's a native of Southwest Virginia. Brian received his BSc in geology from Virginia Tech and MSc and PhD in geochemistry from Penn State and Jacobs University Bremen, respectively. So I will hand it over to Brian, and thank you all for joining today.
Great. Thank you for the introduction, Diane. And thank you to everybody for being part of the webinar today. The title, Environmental Analysis by ICP-MS, is pretty broad. So before we get started, I just want to say that we are going to be staying at a pretty high level for this conversation. The presentation will take about 20 to 25 minutes, after which we should have ample opportunity for any questions that you may have. And what we're going to be focusing on are the limitations or benefits of using ICP-MS in the context of various environmental methods, and in particular, EPA methods such as 60/20 or 200.8. And then we want to talk a little bit about the application of some interference check solutions. If you are familiar with either the EPA methods or some of the others, they all require an assessment of interferences. And then we'll wrap things up at the end with a discussion more focused on chemistry, essentially the chemistry of your sample preparation and also the chemical compatibility and stability of your working solutions. So we'll go ahead and get started. And there we go. So what are we measuring? For the particular methods that we're focused on, the sample types are either going to be a water, and the water could be anything from drinking water to natural waters or wastewater. Other sample types could include solids. The phrases that are typically used are sludge or biosolids, and I think we all know what we're talking about in that regard. But I also tossed in soils, because from my experience, if you're able to measure some of these solid materials that are part of the EPA methods, then you're really going to be able to do a good job on many of the soils that are out there. So if your lab is focused on that, hopefully some of this information will be useful in that context. The different methods, while we're kind of using EPA as a framework, there's a number of other different methods out there, standard methods 3125. And the ASTM method is actually under revision right now, and we are working with that ASTM committee to update that particular approach for environmental analyses as well. I do want to mention right now that we're not going to be discussing collision or reaction cell technologies. The reason is that the instrument manufacturers have a number of different approaches to these technologies. And when you start looking at the details of the individual approaches and specific applications, it gets a little messy. If you have questions about that, we'd be happy to talk about it in greater detail, but we'll save that for after this particular presentation. So what are we measuring? Regardless of whether you're looking at the EPA methods or perhaps standard methods, it's generally going to be about 20 to 25 elements. And from my particular background, I always refer to elements such as sodium, potassium, magnesium, or calcium as the major elements. You can also throw in iron or aluminum occasionally, depending upon your sample type, as being major elements. And then everything else will be minor or trace, which just implies that their concentration in the original sample is going to be well below 1,000 parts per million generally. So I'm a big fan of pictures, and the periodic table that you see on the right is a preferred approach of mine. And when I'm thinking about ICP-MS analyses, I tend to draw a line horizontally through the periodic table between the first and second row transition metals. And the reason I do that is because I've noticed through my experience that once you get above about mass 80, then things get really easy in the ICP-MS world. And so I generally use that as kind of a cutoff when someone would bring me a sample, and I would look at the periodic table and say, what element do you want to measure? If you're above rubidium, molybdenum, things like that, I went, wow, okay, this should be relatively simple. When you're below mass 80, things get a little bit more complicated, and we'll examine that in more detail. So what are some of the benefits or limitations of ICP-MS? One of the great benefits of the technology is how incredibly sensitive it is. And this is something that I think we're all relatively familiar with. This sensitivity is going to be a function of three basic effects: isotopic abundance, ionization energy, and mass bias. We're going to focus on the first two today, the isotopic abundance and the ionization energy. And the chart on the right, I think, does a really nice job of illustrating the effect of isotopic abundance. So what we're looking at are the signal intensities for three different metals: cobalt, nickel, and copper. And the thing to remember is that these are solutions where all of these metals are present at exactly the same concentration of 10 parts per billion. And if we just focus on the nickel and the copper, you can see that the signal intensity is definitely a function of the isotopic abundance. Lower abundance means lower signal intensity, which means that your signal to noise ratio will be lower as well. So if you don't generally think about abundances when you are planning your analyses, I'm going to encourage you to do so. And one of the big reasons is really related to the software of ICP-MSs. They often recommend the most abundant isotope as the preferred isotope to measure. And I think what we're going to see is that you really should use that or take that approach with some caution. So the next thing would be the ionization energy that affects sensitivity. Again, we're looking at a number of metals. In this particular instance, I'm going to ask you to focus on the mercury and the thallium. These two solutions represent mercury and thallium concentrations that are exactly equal. Again, 10 parts per billion. And what we'll see is that you have very different signal to noise ratios, and it's solely due to the ionization energy required to ionize these particular metals. And what's important to note is that for both the 202 isotope for mercury and the 203 isotope for thallium is that they have exactly the same isotopic abundance. So this big discrepancy in the signal intensity is solely due to the ionization energy. For the environmental analyses and the elements that we looked at in a previous slide, this becomes particularly important for elements like arsenic and selenium, which are very, very difficult to measure. And we'll see a little bit more information about that regarding selenium in just a moment. So what's a worst case scenario for ICP-MS when we're looking at environmental analyses? Well, the worst case would be a low mass element that has very low abundance and has a high ionization energy. Even though these two elements are not part of the EPA methods, the prime examples would be phosphorus and sulfur. And those are two elements that generally you want to do with a different method. But because of their low mass, low abundance for some of the isotopes, and the high ionization energy, they can be very challenging for ICP-MS. And again, I'm just going to pick on selenium here. So we're in a part of the mass range where some of your argon chloride interferences start to kick in. And in my experience, my three favorite isotopes for selenium were 76, 77, and 78. They're all minor isotopes, and selenium has a very high ionization energy. So when you couple that with the interferences that you generally find in that part of the mass range, they represent a pretty significant challenge for environmental analyses. So what do you do about interferences? Regardless of the method, whether it's EPA, ASTM, or standard methods, they generally have some passage in the method that says you have to perform an assessment of different interferences. And we have 4 different types of interferences listed here. The isobaric is a great example, and from the previous slide where I mentioned selenium, the 78 isotope for selenium, you have to worry about krypton. You also have molecular interferences, and again, picking on selenium, that could be coming from argon or argon chloride polyatomics. The physical interferences could be things like viscosity, the nebulization efficiency of your sample introduction system, or memory effects such as washout. And all the methods say you can apply interference corrections. Don't worry about this as long as you validate the method, meaning that you have documentation and supporting data that shows that your approach is appropriate and fit for purpose. The nice thing, though, about all these methods is that they also give you the freedom to alter and customize an interference check solution for your application. So you should never feel that you have to follow a specific approach. And I would suggest that you really want to find the method that works best for you. So we're going to now look at some interference check solutions that are commercially available. And we're going to focus on two products that Inorganic Ventures provides. The key thing about an interference check solution is that it's usually going to come in two parts. You're going to get one interference check solution that contains all the things that you don't care about. And I like the term synthetic matrix. So the table on the left shows you what an ICS would be for this synthetic matrix. You'll notice that it has a lot of the major elements and things that aren't in the EPA or the other methods. And so you really don't want to measure these, but they can affect your measurement of other elements that you do care about. And these are found on the table on the right. And the process for performing an interference check is that you would run the synthetic matrix first, measure all the isotopes for all the elements that you do care about, and you generate a baseline. You then mix the two solutions together to determine the effect of the synthetic matrix on your spike solution or all the elements that you really want to get a good number for. One of the things that's absolutely critical when you're doing any interference check assessment is the purity of the material. And if you are going out into the market and purchasing a commercially available standard, you really should expect that manufacturer to provide you with an impurity analysis for these solutions, because that will be critical when you're trying to decide, is this an interference that I'm seeing, or is it perhaps a slight impurity? And so that is a commercially available approach. One of the things that I would caution, though, and say be aware about, is that when you're doing your interference check studies, is that the more complex the matrix, then actually assessing what specific interferences are giving you heartache can be pretty challenging. And the chart on the right is a bit busy, and I'm just going to ask you to focus in on a couple of key points. This shows data when you are measuring mass 59, which is where you would find cobalt, and cobalt is part of these environmental methods. It's monoisotopic, so you don't have any choices. You have to measure mass 59. And what you'll see is that there's two distinct interferences that can affect your measurement at mass 59. One interference is due to calcium and one interference is due to magnesium chloride. So the reason I say that these assessments can be challenging is because if your sample has very different ratios of magnesium to calcium, then you could get different effects at mass 59. And really the way to kind of tease out the truth in this situation is to go back to some single elements. And single element solutions really are your friend when you are doing interference assessments. So our recommendation would be, one, that keep some single element solutions around. And if they expire, that means that they're no longer going to be suitable for analytical determinations. But you can use them for interference studies. Referring back to the previous slide again, purity is critical. So make sure that you have some type of impurity assessment from the manufacturer, which will be super helpful. Now we want to move a little bit into some of the sample preparation effects. So for these methods, there's a number of different approaches that you can use. I imagine that most of you are familiar with many, if not all of these. The best one would be dilute and shoot. Let's say you're measuring potable water. You probably will just acidify a little bit, maybe not dilute at all, and you're done. That's nice. The other approaches include hot block or microwave. From my perspective, I would assume or say that these are essentially the same approach. They may be under pressure, they may not, but essentially you're taking your sample, you're adding some strong mineral acids and some energy, and you get everything into solution as you desire. And then the last one would be a fusion. It doesn't seem that a lot of people are using fusions extensively anymore, but if you are in your lab or you have any questions, we have a great deal of information regarding fusion sample preparation methods, and we could help you troubleshoot a number of different things. Regardless of which one you're choosing, they're all going to require some type of acid at some part in the process. And for the discussion today, we're going to focus on 3 acids: nitric, the most common, HCl, and HF. We understand that many labs cannot use HF, and we'll offer some alternatives in relation to the preparation chemistry for your solutions and standards that will allow you to kind of get around that issue. So, sample preparation effects. Now we're back to my favorite picture of the periodic table, and we're going to see this for a number of slides moving forward. In this example, what I've done is I've taken the 200.8 elements and I've expanded the list a little bit. And I've included elements that you'll find in the EPA method 200.7, which is focused on ICP-MS. And the reason I think this is beneficial is because regardless of your sample preparation, you might have different instruments in your lab that you could choose from. And it's possible that even though you might be solely doing 200.8, in the future, you might expand your element list to include other environmental analytes. So if we group those two methods together and look at the elements that are part of them, this chart is showing you all of the elements that are part of the methods. Those are in the boxes. And then the ones that are highlighted in blue, the nice thing about these elements is that they are absolutely indifferent to which mineral acid that you're using. They're also absolutely indifferent to what other elements you mix them with. So if you only have to measure elements that are in blue, the message would be this: put it in pretty much whatever matrix you want and mix them in any combination that you want, and you're not going to have any problems. However, if you want to kind of expand the list a little bit, one of the things that you would want to consider are the elements that don't like HF. So these would be the alkaline earths and the rare earths and thorium. When I say avoid HF, it's important to qualify that. It doesn't mean that you can't have HF present. It just means that you want to keep the HF relatively low. What does relatively low mean? We have found that about 0.1% volume dilution of HF really doesn't cause any problems for the elements that are highlighted in yellow. It's only when you get to higher concentrations of HF that you really start to run into some issues. And we've also found that 0.1% HF is not, doesn't really do any damage to your sample introduction system. You'll get elevated counts for silicon and sodium, but that would be kind of the recommendation for the amount of HF that you would need to stabilize elements that tend to like it. Now, there are some elements that do like HF. The common ones that are part of this method or these methods would include titanium, molybdenum, tin, and antimony. However, for those 4 metals, you can avoid HF entirely and just use HCl chemistry. So if you have to measure titanium, moly, tin, or antimony, don't worry if you can't use HF in your lab. We can help you kind of design solutions that'll be stable because we'll be focusing on HCl chemistry. However, if you do have HCl, whether it's part of your sample preparation or your method, you want to consider its effect on the 3 elements that are highlighted in red. Many people are aware of the silver chloride precipitation issue. That is a problem, but you can get around that by simply increasing the amount of HCl. In other words, if you have an excess of HCl, then silver is stable in solution. And we have some data there giving an idea of what those limits are. Thallium, this is a bit of a different one. It's perfectly happy in HCl, but only if it's in a +3 oxidation state. You want to contact your supplier and ask them if they are using thallium nitrate or thallium oxide. The nitrate will be +1 you don't want to mix that with HCl because it'll precipitate out like silver. If they're using the oxide as the source for thallium, then you're perfectly okay and you can use HCl. And then lead only has a problem with HCl when the concentrations are relatively high. And for a mass spec application, that's not going to generally be an issue because you can dilute down to a working level where you're not going to have any problems. What about the chemical stability and talking about working standards? So one of the things that we want to focus on is the difference between a working standard that you need to be stable for perhaps days or weeks versus long-term stability. We focus on solutions that'll be stable indefinitely, but is perfectly acceptable for you to prepare working standards in your lab that might only be stable for a day or two, as long as you understand that. And then you can use those very, very quickly and get fantastic results. This working standard here is a bit high for mass spec at 10 ppm, but it could be a great stock solution for you. And again, we have all the elements that were shown in a previous slide. And in 5% nitric with just 0.1% HF, they're all perfectly happy indefinitely. Now you see two elements there are mercury and tin, because they do require special consideration. While tin is only found in the ICP-MS method 6010, mercury is definitely part of the mass spec methods like 200.8. So what do we want to do about those? Well, for tin, you do have a couple of choices. Tin is an HCl element and it will be stable in 10% HCl, or you can go with a HF nitric chemistry. The challenge is going to be if you use the second chemistry of HF and nitric acid, mixing it with alkaline earths, thorium, or the rare earths could be challenging. Mercury is a bit of a different beast, and we receive a lot of technical calls and questions about mercury. It's probably the element that we get the most questions about. So here are some general guidelines. If you are working exclusively in plastic, which is nice because it's clean, then mercury in plastic will have a problem as it can absorb to the container walls. So this is really only an issue, however, at lower concentrations of mercury, where 100 ppm is about the cutoff. If you stay above that concentration, then you can store your mercury solutions in 5% nitric and polyethylene, and you're going to be perfectly happy. Go to lower concentrations, generally below 1 part per million, and you're going to want to stabilize those with gold. And we can talk a little bit more about those details. If you are working in glass, mercury loves it. 5% nitric, doesn't matter what the concentration is, you're good to go. If you are going to go to lower concentrations, and now we're really where mass spec shines, because you might be analyzing solutions where your mercury concentration is well below 1 part per million. In that instance, we would recommend that you go to an HCl matrix, and particularly because at really low concentrations, you probably want to be sticking with plastic labware because it tends to be cleaner than glass. And one thing is that if you are measuring antimony and mercury together, reach out to your supplier for your standards and ask them, how do they stabilize the antimony? Tartrate is the classic chemistry for stabilizing antimony. If it's present, it can reduce mercury, which is an issue. So you want to be aware of kind of what the provenance is or the source of your standards and what the manufacturer might have used to make them. So let's get into some of the summary, the tips and the tricks. For the ICP-MS basics, I would say that one of the key things that I've learned over the years is you really want to know the limitations of the software. The software is much easier to use than it was 20 years ago, and that's fantastic. One of the things I've noticed, however, is that often the software will recommend isotopes, these default isotopes. These tend to be the most abundant isotopes, and in my experience, it's not always the case, and sometimes rarely the case, that those default isotopes suggested by the software are really the best ones to measure. Another thing that you want to understand is how the corrections are applied. If you allow your software to apply the corrections, there's 3 basic types. You might have an internal standard correction, an interference correction, and a blank correction. You want to understand very clearly the math behind how these corrections are applied. Internal standard is generally you're going to want to apply that first, but there's a couple of different ways to do that. Interferences are generally going to be applied second, and then your blank correction would be applied third. But regardless, if you're letting the software do this, I would suggest really digging in so that you understand the mathematical equations that are being used. For interferences, there's one trick that I rely on all the time. It is the go-to for ICP-MS. You use the isotopic abundances to identify your interferences. If there are no interferences present, then you should get the same number when you divide the raw data for an isotope by its isotopic abundance and compare it to the other isotopes for that element. And the example here, I think, illustrates that more clearly. If we look at nickel, 3 isotopes, 60, 61, and 62. Take the raw data and counts per second and divide by the abundance of that isotope expressed as a ratio. If you get the same answer, then you are measuring nickel. And if you get a different answer for one of those, it's probably going to be on the high side. And that's going to be the isotope that's most likely suffering from an interference. What about some tips and tricks for element compatibility and stability? Can you mix everything together? Yeah, you can, but general rule of thumb, lower is better. I will tell you that when you get below 1 part per million, you can put almost the entire periodic table together in a single stable solution. We have a lot of information on our website about how to do that. You want to consider what you can use in your lab. If you cannot use HF, that's okay. There's a number of different approaches that will allow you to obtain fantastic results. Be aware of the starting materials. What is the source for the metal in solution? And the element matrix chemistry that we already discussed. For EPA 200.8 and similar methods, we're just going to say and reiterate that mercury tends to be the element that gives you the most headache. So that wraps up the webinar for today. I hope you found it interesting. Our online resources on our website, we could cover a lot of different things, a lot of great information there. I do also want to mention that this September, we have 2 events that are occurring. We are offering an in-person ICP training at our facility in Christiansburg at the beginning of September. And then a week later, we'll have an online virtual ICP conference that we've been running for a number of years. So if you have any questions, I'd love to hear them, and thank you for your time.
Thank you, Brian. Really appreciate the time today. For all the folks that are on the phone, we will be sharing the slides as well as Brian's contact information if you have any follow-up questions in regards to this. And we really appreciate you taking some time out here today to learn a little bit more about this, and have a wonderful afternoon.